Part 2, Chapter 4 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Part 2, Chapter 4, Solar Spectroscopy, Part 2. As to vertical motions above the limb, on the other hand, we have direct visual evidence of a truly amazing kind. The projected glowing matter has, by the aid of the spectroscope, been watched in its ascent. On September 7, 1871, Young examined at noon a vast hydrogen cloud 100,000 miles long, as it showed to the eye, and 54,000 high. It floated tranquilly above the chromosphere at an elevation of some 15,000 miles, and was connected with it by 3 or 4 upright columns, presenting the not uncommon aspect compared by Lockyer to a grove of banyans. Called away for a few minutes at 12:30, on returning at 12:55, the observer found that in the meantime the whole thing had been literally blown to shreds by some inconceivable uprush from beneath. In place of the quiet cloud I had left, the air, if I may use the expression, was filled with flying debris, a mass of detached, vertical, fusiform filaments, each from 10 feet to 30 feet by 2 or 3 feet wide, brighter and closer together where the pillars had formerly stood, and rapidly ascending. They rose, with a velocity estimated at 166 miles a second, to fully 200,000 miles above the sun's surface, then gradually faded away like a dissolving cloud, and at 1:15 only a few filmy wisps, with some brighter streamers low down near the photosphere, remained to mark the place. A velocity projection of at least 500 miles per second was, by Proctor's calculation, required to account for this extraordinary display, to which the earth immediately responded by a magnetic disturbance and a fine aurora. It has proved by no means an isolated occurrence. Young saw its main features repeated October 7, 1881, on a still vaster scale, for the exploded prominence attained this time an altitude of 350,000 miles, the highest yet chronicled. Lockyer, moreover, has seen a prominence 40,000 miles high shattered in 10 minutes, while uprushes have been witnessed by Respighi, of which the initial velocities were judged by him to be 400 or 500 miles a second. When it is remembered that a body starting from the sun's surface at the rate of 383 miles a second would, if it encountered no resistance, escape forever from his control, it is obvious that we have, in the enormous forces of eruption or repulsion manifested in the outbursts just described, the means of accounting for the vast diffusion of matter in the solar neighborhood. Nor is it possible to explain them away, as Cornu, Faye, and others have sought to do, by substituting for the rush of matter in motion progressive illumination through electric discharges, chemical processes, or even through the mere reheating of gases cooled by expansion. All the appearances are against such evasions of the difficulty presented by velocities stigmatized as fabulous and improbable, but which there is the strongest reason to believe really exist. On the 12th of December, 1878, Sir Norman Lockyer formally expounded before the Royal Society his hypothesis of the compound nature of the chemical elements, a hypothesis, it is true, over and over again propounded from the simply terrestrial point of view. What was novel was the supra-terrestrial evidence adduced in its support, and even this had been, in a general and speculative way, anticipated by Professor F. W. Clarke of Washington. Lockyer had been led to his conclusion along several converging lines of research. In a letter to M. Dumas, dated December 3, 1873, he had sketched out the successive stages of celestial dissociation, which he conceived to be represented in the sun and stars. The absence from the solar spectrum of metalloidal absorption he explained by the separation, in the fierce solar furnace, of such substances as oxygen, nitrogen, sulfur, and chlorine into simpler constituents possessing unknown spectra, while metals were at that time still admitted to be capable of existing there in a state of integrity. 3 years later he shifted his position onward. He announced, as the result of a comparative study of the Fraunhofer and electric arc spectra of calcium, that the molecular grouping of that metal, which at low temperatures gives a spectrum with its chief line in the blue, is nearly broken up in the sun into another or others with lines in the violet. This came to be regarded by him as a truly typical case. During 4 years, 1875 to 78 inclusive, this diligent observer was engaged in mapping a section of the more refrangible part of the solar spectrum, wavelengths of 3,800 to 4,000, on a scale of magnitude such that, if completed down to the infrared, its length would have been about half a furlong. The attendant laborious investigation, by the aid of photography, of metallic spectra, seemed to indicate the existence of what he called basic lines. These held their ground persistently in the spectra of 2 or more metals after all possible impurities had been eliminated, and were therefore held to attest the presence of a common substratum of matter in a simpler state of agitation than any with which we are ordinarily acquainted. Later inquiries have shown, however, that between the spectral lines of different substances there are probably no absolute coincidences. Basic lines are really formed of doublets or triplets merged together by insufficient dispersion. Of Thalin's original list of 70 rays common to several spectra, very few resisted Thollon's and Young's powerful spectroscopes, and the process of resolution was completed by Rowland. Thus the argument from community of lines to community of substance has virtually collapsed. It was replaced by one founded on certain periodical changes on the spectra of sunspots. They emerged from a series of observations begun at South Kensington under Sir Norman Lockyer's direction in 1879 and continued for 15 years. The principle of the method employed is this: the whole range of Fraunhofer lines is visible when the light from a spot is examined with the spectroscope, but relatively few are widened. Now these widened lines alone constitute, presumably, the true spot spectrum. They and they alone tell what kinds of vapor are thrust down into the strange dusky pit of the nucleus, the unaffected lines taking their accustomed origin from the overlying strata of the normal solar atmosphere. Here, then, we have the criterion that was wanted, the means of distinguishing, spectroscopically and chemically, between the cavity and the absorbing layers piled up above it. By its persistent employment, some marked peculiarities have been brought out, such as the unfamiliar character of numerous lines in spot spectra, especially at epochs of disturbance, and the strange individuality in the behavior of every one of these darkened and distended rays. Each seems to act on its own account. It comports itself as if it were the sole representative of the substance emitting it. Its appearance is unconditioned by that of any of its terrestrial companions in the same spectrum. The most curious fact, however, elicited by these inquiries was that of the attendance of chemical vicissitudes upon the advance of the sunspot period. As the maximum approached, unknown replaced known components of the spot spectra in a most pronounced and unmistakable way. It seemed as if the vapors emitting lines of iron, titanium, nickel, etc., had ceased to exist as such, and their room been taken by others, total strangers in terrestrial laboratories. These were held by Lockyer to be simply the finer constituents of their predecessors, dissociation having been effected by the higher temperature ensuing upon increased solar activity. But Father Cordy's supplementary investigations at Stonyhurst modified, while they in the main substantiated, the South Kensington results. They showed that the substitution of unknown for known lines characterizes disturbed spots at all stages of the solar cycle, so that no systematic course of chemical change can be said to affect the sun as a whole. They showed further, from evidence independent of that obtained by Young in 1892, the remarkable conspicuousness in spot spectra of vanadium lines excessively faint in the Fraunhofer spectrum. Lockyer's unknown lines may probably thus be accounted for. They represent absorption, not by new but by scarce elements, especially, Father Cordy thinks, those with atomic weights of about 50. The circumstance of their development in solar commotions, largely to the exclusion of iron, is none the less curious, but it cannot be explained by any process of dissociation. The theory has, however, to be considered under still another aspect. It frequently happens that the contortions or displacements due to motion are seen to affect a single line belonging to a particular substance, while the other lines of that same substance remain imperturbable. Now, how is this most singular fact, which seems at first sight to imply that a body may be at rest and in motion at one and the same instant, to be accounted for? It is accounted for, on the present hypothesis, easily enough, by supposing that the rays thus discrepant in their testimony do not belong to one kind of matter, but to several, combined at ordinary temperatures to form a body in appearance elementary. Of these different vapors, one or more may, of course, be rushing rapidly towards or from the observer, while the others remain still, and since the line of sight across the average prominence region penetrates at the sun's edge a depth of about 300,000 miles, all the incandescent materials separately occurring along which line are projected into a single flame or cloud, it will be perceived that there is ample room for diversities of behavior. The alternative mode of escape from the perplexity consists in assuming that the vapor in motion is rendered luminous under conditions which reduce its spectrum to a few rays, the unaffected lines being derived from a totally distinct mass of the same substance shining with its ordinary emissions. Thus calcium can be rendered virtually monochromatic by attenuation, and analogous cases are not rare. Sir Norman Lockyer only asks us to believe that effects which follow certain causes on the earth are carried a stage farther in the sun, while the same causes must be vastly intensified. We find that the bodies we call compound split asunder at fixed degrees of heat within the range of our resources. Why should we hesitate to admit that the bodies we call simple do likewise at degrees of heat without the range of our resources? The term element simply expresses terrestrial incapability of reduction. That in celestial laboratories the means and their effect here absent should be present would be an inference challenging in itself no expression of incredulity. There are indeed theoretical objections to which, though probably not insuperable, are unquestionably grave. Our 70 chemical elements, for instance, are placed by the law of specific heats on a separate footing from their known compounds. We are not, it is true, compelled by it to believe their atoms to be really and absolutely such, to contain, that is, the irreducible minimum of material substance, but we do certainly gather from it that they are composed on a different principle from the salts and oxides made and unmade at pleasure by chemists. Then the multiplication of the species of matter with which Lockyer's results menace us is at first sight startling. They may lead, we are told, to eventual unification, but the prospect appears remote. Their only obvious outcome is the disruption into several constituents of each terrestrial element. The components of iron alone should be counted by the dozen. And there are other metals, such as cerium, which, giving a still more complex spectrum, would doubtless be still more numerously resolved. Sir Norman Lockyer interprets the observed phenomena as indicating the successive combinations in varying proportions of a very few original ingredients, but no definite sign of their existence is perceptible. Protyle seems long to evade recognition, and the only intelligible underlying principle for the reasonings employed, that of one line, one element, implies a throng beyond counting of formative material units. Thus, added complexity is substituted for that fundamental unity of matter which has long formed the dream of speculators, and it is extremely remarkable that Sir William Crookes, working along totally different lines, has been led to analogous conclusions. To take only one example, as the outcome of extremely delicate operations of sifting and testing carried on for years, he finds that the metal yttrium splits up into 5, if not 8 constituents. Evidently, old notions are doomed, nor are any preconceived ones likely to take their place. It would seem, on the contrary, as if their complete reconstruction were at hand. Subversive facts are steadily accumulating. The revolutionary ideas springing from them tend, if we interpret them aright, towards the substitution of electrical for chemical theories of matter. Dissociation by the brute force of heat is already nearly superseded, in the thoughts of physicists, by the more delicate process of ionization. Precisely what this implies and involves we do not know, but the symptoms of its occurrence are probably altogether different from those gathered by Sir Norman Lockyer from the collation of celestial spectra. A. J. Ångström of Uppsala takes rank after Kirchhoff as a subordinate founder, so to speak, of solar spectroscopy. His great map of the normal solar spectrum was published in 1868, 2 years before he died. Robert Thalèn was his coadjutor in its execution, and the immense labor which it cost was amply repaid by its eminent and lasting usefulness. For more than a score of years it held its ground as the universal standard of reference in all spectroscopic inquiries within the range of the visible emanations. Those that are invisible, by reason of the quickness of their vibrations, were mapped by Dr. Henry Draper, of New York, in 1873, and with superior accuracy by M. Cornu in 1881. The infrared part of the spectrum, investigated by Langley, Abney, and Knut Ångström, reaches perhaps no definite end, the radiations oscillating too slowly to affect the eye, as light may pass by insensible gradations by the long Hertzian waves of electricity. Professor Rowland's photographic map of the solar spectrum, published in 1886, and a second enlarged edition in 1889, opened fresh possibilities for its study, from far down in the red to high up in the ultraviolet, and the accompanying scale of absolute wave lengths has been, with trifling modifications, universally adopted. His new table of standard solar lines was published in 1893. Through his work, indeed, knowledge of the solar spectrum so far outstripped knowledge of terrestrial spectra that the recognition of their common constituents was hampered by intolerable uncertainties. Thousands of solar lines charted with minute precision remained unidentified for want of a corresponding precision in the registration of metallic lines. Rowland himself, however, undertook to provide a remedy. Aided by Louis E. Jewell, he redetermined at Johns Hopkins University the wavelengths of about 16,000 solar lines, photographing for comparison with them the spectra of all known chemical elements except gallium, of which he could procure no specimen. The labor of collation was well advanced when he died at the age of 52, April 16, 1901. Investigations of metallic arc spectra have also been carried out with signal success by Hasselberg, Kayser, and Runge, O. Lohse, and others. Another condition sine qua non of progress in this department is the separation of true solar lines from those produced by absorption in our own atmosphere, and here little remains to be done. Tholen's great atlas was designed for this purpose of discrimination. Each of its 33 maps exhibits, in quadruplet, a subdivision of the solar spectrum under varied conditions of weather and zenith distance. Telluric effects are thus made easily legible, and they account wholly for 866, partly for 246, out of a total of 3,200 lines. But the death of the artist, April 8, 1887, unfortunately interrupted the half-finished task of the last 7 years of his life. A most satisfactory record, meanwhile, of selective atmospheric action has been supplied by the experiments and determinations of Janssen, Cornu, and Egorov, by Dr. Becker's drawings, and Mr. Maclean's photographs of the analyzed light of the sun at high, low, and medium altitudes, and the autographic pictures obtained by Mr. George Higgs of Liverpool of certain rhythmical groups in the red, emerging with surprising strength near sunset, excite general and well-deserved admiration. The main interest, however, of all these documents resides in the information afforded by them regarding the chemistry of the sun. The discovery that hydrogen exists in the atmosphere of the sun was made by Ångström in 1862. His list of solar elements published in that year, the result of an investigation separate from, though conducted on the same principle as Kirchhoff's, included the substance which we now know to be predominant among them. Dr. Plücker of Bonn had identified in 1859 the Fraunhofer line F with the green ray of hydrogen, but drew no inference from his observation. The agreement was verified by Ångström, two further coincidences were established, and in 1866 a fourth hydrogen line in the extreme violet, named h, was detected in the solar spectrum. With Thalin, he besides added manganese, titanium, and cobalt to the constituents of the sun enumerated by Kirchhoff, and raised the number of identical rays in the solar and terrestrial spectra of iron to no less than 460. Thus, when Sir Norman Lockyer entered on that branch of inquiry in 1872, 14 substances were recognized as common to the earth and sun. Early in 1878, he was able to increase the list provisionally to 33, all except hydrogen metals. This rapid success was due to his adoption of the test of length in lieu of that of strength in the comparison of lines. He measured their relative significance, in other words, rather by their persistence through a wide range of temperature than by their brilliance at any one temperature. The distinction was easily drawn. Photographs of the electric arc, in which any given metal had been volatilized, showed some of the rays emitted by its stretching across the axis of the light to a considerable distance on either side, while many others clung more or less closely to its central hottest core. The former long lines, regarded as certainly representative, were those primarily sought in the solar spectrum, while the attendant short lines, often in point of fact due to foreign admixtures, were set aside as likely to be misleading. The criterion is a valuable one, and its employment has greatly helped to quicken the progress of solar chemistry. Carbon was the first non-metallic element discovered in the sun. Messrs. Trowbridge and Hutchins of Harvard College concluded in 1887, on the ground of certain spectral coincidences, that this protein substance is vaporized in the solar atmosphere at a temperature approximately that of the voltaic arc. Partial evidence to the same effect had earlier been alleged by Lockyer, as well as by Liveling and Dewar, and the case was rendered tolerably complete by photographs taken by Kayser and Runge in 1889. It was by Professor Rowland shown to be irresistible. 200 carbon lines were, through his comparisons, sifted out from sunlight, and it contained others significant of the presence of silicon, a related substance, and one as important to rock building on the earth as carbon is to the maintenance of life. The general result of Rowland's labors was the establishment among solar materials not only of these two out of the 14 metalloids, or non-metallic substances, but of 33 metals, including silver and tin. Gold, mercury, bismuth, antimony, and arsenic were discarded from the catalogue. Platinum and uranium, with 6 other metals, remained doubtful, while iron was recorded as crowding the spectrum with over 2,000 obscure rays. Gallium absorption was detected in it by Hartley and Ramage in 1889. Dr. Henry Draper announced in 1877 his imagined discovery in the solar spectrum of 18 especially brilliant spaces corresponding to oxygen emissions, but the agreement proved, when put to the test of very high dispersion, to be wholly illusory. Nor has it yet been found possible to identify in analyzed sunlight any significant bright beams. The book of solar chemistry must be read in characters exclusively of absorption. Nevertheless, the whole truth is unlikely to be written there. That a substance displays none of its distinctive beams in the spectrum of the sun or of a star affords scarcely a presumption against its presence, for it may be situated below the level where absorption occurs, or under a pressure such as to efface lines by widening and weakening them. It may be at a temperature so high that it gives off more light than it takes up, and yet its incandescence may be masked by the absorption of other bodies. Finally, it may just balance absorption by emission with the result of complete spectral neutrality. An instructive example is that of the chromospheric element helium. Father Secchi remarked in 1868 that there is no dark line in the solar spectrum matching its light, and his observation has been fully confirmed. Helium absorption is, however, occasionally noticed in the penumbrae of spots. Our terrestrial vital element might then easily subsist unrecognizably in the sun. The inner organization of the oxygen molecule is a considerably plastic one. It is readily modified by heat, and these modifications are reflected in its varying modes of radiating light. Dr. Schuster enumerated in 1879 4 distinct oxygen spectra, corresponding to various stages of temperature or phases of electrical excitement, and a fifth has been added by M. Egoroff's discovery in 1883 that certain well-known groups of dark lines in the red end of the solar spectrum, Fraunhofer's A and B, are due to absorption by the cool oxygen of our air. These persist down to the lowest temperatures and even survive a change of state. They are produced essentially the same by liquid as by aerial oxygen. It seemed, however, possible to M. Janssen that these bands owned a joint solar and terrestrial origin. Oxygen in a fit condition to produce them might, he considered, exist in the outer atmosphere of the sun, and he resolved to decide the point. No one could bring more skill and experience to bear upon it than he. By observations on the summit of the Faulhorn, as well as by direct experiment, he demonstrated, nearly 30 years ago, the leading part played by water vapor in generating the atmospheric spectrum, and he had recourse to similar means for appraising the share in it assignable to oxygen. An electric beam, transmitted from the Eiffel Tower to Meudon in the summer of 1888, having passed through a weight of oxygen about equal to that piled above the surface of the earth, showed that groups A and B, just as they appear in the high sun spectrum. Atmospheric action is then adequate to produce them. But M. Janssen desired to prove, in addition, that they diminish proportionately to its amount. His ascent of Mont Blanc in 1890 was undertaken with this object. It was perfectly successful. In the solar spectrum, examined from that eminence, oxygen absorption was so much enfeebled as to leave no possible doubt of its purely telluric origin. Under another form, nevertheless, it has been detected as indubitably solar. A triplet of dark lines, low down in the red, photographed from the sun by Higgs and Maclean, was clearly identified by Runge and Paskin in 1896 with the fundamental group of an oxygen series, first seen by Piazzi Smyth in the spectrum of a vacuum tube in 1883. The pabulum vitae of our earth is then to some slight extent effective in arresting transmitted sunlight, and oxygen must be classed as a solar element. The rays of the sun, besides being stopped selectively in our atmosphere, suffer also a marked general absorption. This tells chiefly upon the slowest wave lengths. The ultraviolet spectrum is in fact closed, if by the interposition of an opaque screen. Nor does the screen appear very sensibly less opaque from an elevation of 10,000 feet. Dr. Simony's spectral photographs, taken on the peak of Teneriffe, extended but slightly further up than M. Cornu's, taken in the valley of the Loire. Could the veil be withdrawn, some indications as to the originating temperature of the solar spectrum might be gathered from its range, since the proportion of quick vibrations given out by a glowing body grows with the intensity of its incandescence, and this brings us to the subject of our next chapter. End of chapter 4, part 2.